Hello and welcome back to Science. Today's PowerPoint, we're going to take a look at the phase change lab that you saw, give some explanations to that, and introduce just a couple new concepts. If you were in class today, we would be starting with a question of the day. This will be up on the board. I'd ask you to be working on this. If you want, I want you to pause the video right now and try to answer this question for yourself. Why does blowing on hot food cool it down so quickly? My daughter has understood this one since the time she was 1. She's known that you blow on hot food, it cools it down. Do we know why that happens? Pause now and answer in your notebook. Answer will be coming at the end of this PowerPoint or near the end of this PowerPoint. Okay, so to review what happened in our phase change lab. The question was, what was happening in those sections of the graphs that were flat? If you recall, the beaker was on a hot plate, and the hot plate was definitely adding energy to the water. But the temperature was not going up. Why not? Well, even though the temperature was not changing, the phase of matter was changing. If you recall, our definition of energy, or one of our explanations of energy, was that it is something for tracking changes in a system. Changing phase is a pretty significant change, even though the temperature is not changing. Our evidence was, well, in that first flat spot, we saw that ice melting. Painfully slowly, but it was a lot faster for you than it was for me. And in the second flat spot, we had the water boiling off. And we know that some of it changed to a gas. Besides seeing the bubbles that were happening, we saw that the level of the liquid water was much lower at the end. Remember, it takes energy to go from a solid to liquid to make that phase change. And it takes even more to go from a liquid to a gas. So here we see a phase change graph, or phase graph, heating curve, some might call it, for water. This one is specifically for water. And in this one, we're starting with ice. Ice that's very cold. Looks like it's at around 25 degrees below 0 Celsius. From A to B on this graph, as energy is being added, the temperature is the first thing that goes up. The temperature of the ice is the first thing that changes. It doesn't start melting right away. It has to warm up to 0 degrees Celsius. And then from B to C, energy is still being put in at a constant rate, but that energy is going into melting the ice. When we get to C, all of the ice has finally melted. We have complete liquid, and then we see the temperature change happening again. That happens until we reach 100 degrees Celsius for water under normal conditions, at which time it is boiling off. It is vaporizing, changing from a liquid into a gas. Interesting on this graph that this flat spot is really, really long. That's not an accident. We'll get to that a little later in this PowerPoint. If you were to leave that pot of water or keep adding enough energy for a long enough period of time, you would finally get to the point where all of the liquid had turned to gas. At that point, you would start heating up that gas, heating that steam, if we could somehow capture it in a container that, as it was boiling off, the gas stayed. Note that in that weird container, the gas would stay at 100 degrees Celsius until all of the water was boiled off. And then, and only then, would the temperature start to increase. And this one I have no numbers on because this is for any material. And the amazing part is this is true for almost any pure material. So we'll say it's true of any pure material. If it is below, it starts out as a complete solid until you get to some point where the temperature does not change, where it is both solid and liquid. Once it is all turned to liquid, the temperature would increase. We get to a point where it is vaporizing, boiling, changing from liquid to gas. And then once it is all gas, the temperature would increase. Now, it turns out this temperature, where it changes from a liquid to a gas, there's a name for that. You probably already know that name. Wait for it. That's right. It's called the boiling point. This flat spot, the temperature at which this occurs, there also is a name for that. Actually, there's two names for this one. Do you know both of those names? Take a moment to write them down, make a prediction for yourself. Those names are the melting point and the freezing point. Now you're saying, how could this possibly be both the melting point and the freezing point? Well, it depends on which way we're going with this curve. If we are adding energy to the material, then that means we started as a solid, and when we get to this point, it is melting as it changes from a solid to a liquid. Then the liquid increases in temperature until we get to the boiling point. Things shown in blue here, though, as you cool that gas down, you end up with condensation happening rapidly at this temperature. I suppose it could be called the condensation point. It's a little bit trickier. There's something called a dew point. If you're really interested, do a little research on that. I'm not going over that now. As the liquid cools and cools and cools, you get to a point where it will, instead of dropping in temperature, it will remain a solid for a while, giving off energy it will remain at the same temperature for a while, giving off energy while it changes from a liquid to a solid. That is called the freezing point. This is why lakes, as they freeze, are actually a little bit warmer to be near them compared to the other air, because the lake is dumping some energy into the air as it's turning from a liquid to a solid. So, if we're in class, this would be a whiteboard question for you. Why don't you take 90 seconds to answer this for yourself? Just pause the video, take a little bit. There are 3 different answers that we're looking for. You'd have a couple minutes to work with your group to do this. Take just 60 to 90 seconds right now to try and answer that for yourself. Coming back in 3, 2, 1. So one of the things that would be different for different materials is that the temperature of the flat spots would change. In other words, the boiling point and the melting freezing point are different for different materials. That makes sense. We know that the melting point for candle wax must be higher than it is for water because it's above room temperature. Another thing that would probably change would be the steepness of those slopes. If you got that, nicely done. If you knew that that's based on the specific heat of the material, you really rock. That's good that you remembered that concept. The last thing that might be different would likely be the length of those flat sections, because that's based on how much energy it takes to melt or boil a material. And in fact, that brings us to our next little concept here. The amount of energy it takes to melt a kilogram of material has a fancy name. It's called the heat of fusion. Not sure why it's not the heat of melting. I don't know. It's called the heat of fusion. The other one, the heat of vaporization, refers to the amount of energy it takes to vaporize or boil 1 kilogram of material. We'd be going into these more in depth if we were in the classroom. For right now, we're just going to touch on this, but I do want to show this graph right here. What this graph is doing for us is showing us the numbers that go for water. I would not want you to memorize these numbers, but I do want you to see what they look like, because this is kind of fascinating to me. Melting water takes 300, we'll just use the number 334, whatever those units are, kilojoules for every kilogram. To change it, once it's completely melted, to change it from 0 all the way up to 100 only takes 418 kilojoules. So it's only a little bit more to change its temperature from the freezing point all the way up to the boiling point. If you consider that your body temperature is only 37 degrees Celsius, then if you are stranded, or if you're in the winter and you eat snow or eat ice, you actually spend twice as much energy in melting the ice than you do in bringing that newly melted water up to the temperature of your body, which is right about here. So that's why in survival situations they tell you, do not eat snow, do not eat the ice, because it will lead to hypothermia much quicker. Find some sort of liquid, even if it's liquid at 0 degrees Celsius, it'll take 1/3 the amount of your thermal energy to bring it up to your body temperature. You'll also notice that this vaporization is very big. It takes 5 times the amount of energy to boil off that water as it did to bring it from 0 up to 100. That to me is really amazing. And it kind of leads to a question for me. Why is the heat of vaporization so much larger than the heat of fusion? In other words, why does it take so much more energy to boil off that water than it did to melt it? And the answer comes in that it takes a lot of energy to change from a liquid to a gas compared to changing from a solid to a liquid. Think of it this way. Changing from a solid to a liquid, you just need to have enough energy to be able to start moving around compared to your neighbors. When you change to a gas, you need to have enough energy to actually completely break away from the rest of the group. It takes a lot of energy to be able to do just that. So that brings us to our question of the day. Why does blowing on hot food cool it down so quickly? It's actually a little bit more than just you're blowing cool air on it. Because if you think about it, even when you have something close to your mouth where you're blowing your warm breath on it, it still cools down quite quickly. And it comes down to that water that's in the food is evaporating. As that water evaporates, it takes a lot of energy with it. It's only the highest energy particles that are going to evaporate. So when they go with a lot of energy, they lower the average kinetic energy of the particles that are remaining. And that means you're lowering the temperature of what is left. What blowing on the food does is increases the evaporation rate. We're not going to get into the reasons for that right now. I will point out, though, that this is also, when we go back to that thermos question, probably the most important aspect of a thermos when it comes to a hot liquid is the cover, because you are stopping that evaporative cooling, or at least you're greatly slowing down the evaporative cooling that's associated with a hot liquid. So covering it in some way really, really helps. To be real clear, you're not completely stopping the evaporation, but you are bringing it into a state of equilibrium with the evaporation and the condensation. For our purposes, you are stopping the evaporative cooling loss by putting a cover on something. Which brings us to an extra credit opportunity. I'm going to make a claim here. A covered pot of water will boil in less time than an uncovered pot of water. That is my claim. What I'd like you to do is design an experiment to test this claim. As you do this, you'd consider all the variables you would need to keep constant. Now, some of you are stressing out, hey, you didn't post this assignment. Okay, you're right. Describe how you would conduct this experiment. So design it, consider those variables, describe this in detail. Do that for extra credit. If you want double extra credit, go ahead and perform the experiment and report your results. Double extra credit, man, that's awesome. Double the learning opportunities. That's right. And stop laughing, I'm serious. It's a good experiment, it's worth doing. Try it out. So, summarizing one more quick glance at this type of a graph. We'll see how this one shows. We have solid here, we have all liquid here, we have all gas right here. This is incorporating those particle diagrams. As energy is being added, the solid is warming here, it's melting here. The liquid is warming here, it's boiling here. The gas would be warming in this section. If you're removing energy, we'd have cooling, condensing, cooling, freezing, and cooling. You will need this concept for the homework. The homework will be for the next 2 days, so it'll be for Thursday and Friday. So that'll wrap up this week. Only 2 weeks to go after this, guys. You're doing great. Stick with it. The last 2 weeks are going to be full of a lot of pressure. It's more in a science aspect than it is in a psychological aspect, I hope. Till then, have a great day. Take care.